This is part 7 of a series on XGBoost. In this video, we'll look at the approximate algorithm for split finding. The video was produced in Korean and translated into English, and my voice was generated through AI, text-to-speech. In the previous videos, we looked at the exact greedy algorithm for regression and classification. This algorithm has the advantage of being able to find accurate optimal split points. However, if there is a lot of data, it takes a long time, and if the data is too large to fit all in memory, the optimal split points cannot be found. In the paper, the approximate algorithm and weighted quantile sketch algorithm were proposed to solve this problem. In this video, we will look at the approximate algorithm and implement it in code to see the effects of this algorithm. First, let's look at what was presented in the XGBoost paper. In Chapter 2, the exact greedy algorithm for split finding is presented as Algorithm 1. Chapter 3 introduces split finding algorithms, and Section 3.2 introduces the approximate algorithm. The exact greedy algorithm is very powerful, since it enumerates over all possible splitting points greedily. However, it is impossible to efficiently do so when the data does not fit entirely into memory. And Section 3.3 introduces the weighted quantile sketch algorithm. We'll look at this algorithm in the next video. In this video, we will look at the Algorithm 2, approximate algorithm for split finding. Let's take a look at the approximate algorithm presented in Section 3.2 of the paper. As mentioned earlier, if you have a lot of data, you can use the approximate algorithm to find approximate split points. Let's use the data below. There are 3 feature X, and there is a target Y. And there is residual like this. Our goal is to find the best feature among these 3 features and find the best split point. Let's take a step-by-step look at how this algorithm works. Calculate the residuals using the previous predictions. In the first iteration round, the initial prediction is used as the previous prediction. The next step is to read the features one by one. The feature vector is like this. Step 3 sorts the feature vector in ascending order. Let's call this variable Sx. Step 4 divides Sx into 1 over epsilon parts. For example, if the epsilon is 0.2, the Sx is divided into 5 parts. The picture on the right is a drawing of the feature X1 and the target Y. Divide this data into 5 buckets. For the first data point, X1 is 0.72, so it falls into the bucket 4. For the second data point, X1 is 0.05, so it falls into the bucket 1. The target Y for every data point in X1 is shown in the following figure. Let's assume our initial prediction is this straight line. The residual sizes of the data points in the bucket 1 are about this sizes. There are a lot of positive residuals. And the bucket 3 has a similar mix of positive and negative residuals. The Sx vector is like this. sorted in ascending order. In step 5, data points are assigned to each bucket. Each bucket contains the same number of data points. In step 6, one thread is assigned to each bucket. Each thread uses the data points in its bucket to calculate the gain. Thread 1 uses the data points in bucket 1 to find the best split point for the bucket 1. Thread 2 uses the data points in bucket 2 to find the best split point for that bucket. Each thread is independent of each other. Therefore, each thread can run in parallel. Step 7 finds the largest gain among the gains found across the 5 threads. This is the optimal split point for the entire X. If the split point found in thread 3 has the largest gain, that split point is selected as the best split point for the entire feature X1. Bucket number 3 has the greatest gain because the residuals before the split cancel each other out. And there is not much of a cancellation after the split. Once processing of one feature is complete, the same is done for the other features. Then, select one of the 3 features with the largest gain. In this way, select the final best feature and the best split point. This is the approximate algorithm. Approximate algorithm has 2 modes, global variant and local variant. In the initial node split, if the epsilon is 0.01, the data is divided into 100 buckets. Each of the 100 threads then finds the optimal split point for each bucket. Now let's think about the next node split. If the initial node split is done in the middle bucket, the root node will be split into left and right, like this. Then the left node will have 51 or 50 buckets, and the right node will have 50 or 51 buckets. Global variant splits each child node using 51 or 50 buckets in the next node split. And the next child node is split into 21 buckets and 30 buckets, like this, for example. In the global variant, the deeper the tree, the smaller the number of buckets. Therefore, it is necessary to set the epsilon sufficiently small. Local variant newly applies the epsilon to child nodes on the next node split. This creates another 100 buckets for each child node. For each node split, for every 100 buckets, 100 threads, find each split point. In this method, even as the tree gets deeper, the number of buckets remains constant at 100. Therefore, we can set the epsilon to be somewhat larger. Let's check the performance of the global and local variant presented in Figure 3 of the paper. The red curve is for global variant and has the epsilon of 0.3. This performance is measured by ROC AUC. Light blue is for the local variant and has the epsilon of 0.3. If the epsilon is the same, you can see that the performance of the local variant is better than that of the global variant. Purple is for the global variant and has the epsilon of 0.05. If we set the epsilon of the global variant to be small, we can see that the performance is similar to that of the local variant. This time, we will look at the algorithm 2, approximate algorithm for split finding, presented in the paper. D is the number of features. Read feature vectors one by one and divide a feature vector by percentile. For example, if the epsilon is 0.2, you can set the percentiles this way so that each bucket contains 20% of the data points. This will create 5 buckets. And use global or local variant. Next, read the feature vectors again one by one. We then calculate G and H using the data points in the bucket where the data points are greater than V-1 and less than V. We then use these G and H to calculate the gain and use the gain to find the optimal split point for this bucket. The thread responsible for this bucket performs these tasks. The subsequent process is the same as seen on the previous page. Now let's simply implement Approximate Algorithm with code and see how it works. Let's use the MyXGBoost class created in this video. The data used in this video is like this. We created 50,000 pieces of this data. First, let's do the exact greedy algorithm. MyXGBoost works with exact greedy algorithm by default. We create a model and fit it to the training data. For simple verification, we set both the number of trees and the depth of the tree to 1. The result of this model is in the Estimator2 dictionary. Let's check the split point and the gain in this dictionary. And let's also check the running time. Next, let's perform the approximate algorithm with the same data. Let's use multiprocessing. Write a function that performs the exact greedy algorithm on the left. Each thread executes this function. The data for this function are the data points that belong to a bucket. The MyXGBoost class is used the same as the left, and the number of trees and the depth are also set the same as the left. Fit this model to the data points in the bucket and see the split point and gain. Set the epsilon to 0.2 and divide the data into 5 buckets. We then allocate 20% of the data points to each bucket. It was coded like this using the NumPy's percentile function. We then assign each data point to its corresponding bucket. This is the data in the first bucket. Now assign 5 processes, and each thread will analyze the data in each bucket. Each thread uses this data to execute this function defined above. This function will then return the split point and the gain. And check the results. Let's check the running time as well. Let's also check the number of data points assigned to each bucket. The results are as follows. The best split point found by the exact greedy algorithm is 0.502. And the running time is 6.2 seconds. For the approximate algorithm, the best split points for each bucket found by the 5 threads are as follows. And the gain list is like this. Of these gains, the third bucket has the largest gain. Therefore, this split point found by the third thread is selected as the best point for the entire data. The best split point is similar to that of the exact greedy algorithm. The running time is 0.27 seconds. You can see that it is much faster than the exact greedy algorithm. And the number of data points in each bucket is the same, 1,000. Again, the MyXGBoost class works with the exact greedy algorithm by default. To correctly implement the approximate algorithm, You must implement it within the MyXGBregressor class. Let's try to run this code. The results are as follows. The best split point found by the exact greedy algorithm is 0.496, and the running time is 6.3 seconds. The best split point found by the approximate algorithm is 0.496 as well. We get the same result as the exact greedy algorithm, and the running time is 0.3 seconds. So far, we have looked at the approximate algorithm, and we have briefly implemented the code to see the effects of this algorithm. In the next video, we will look at the weighted quantile sketch algorithm.